Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 13. In this lecture, we'll discuss sound energy and power. These topics are covered in Chapter 17 of our textbook by Surway and Jouet. Sound waves, like all waves, carry energy, and the amount of energy that they carry is going to be important to us. More specifically, we're interested in the power of sound waves. Recall that power is the rate of energy transfer, so the amount of energy that is transferred or converted per unit of time is referred to as power. To understand the power of sound waves, we'll begin with a description of the displacement of molecules. So recall that the displacement of a molecule that is normally located at coordinate x at a particular time t is given by this function here. S max is the amplitude or the maximum displacement of the oscillation. The sine function usually involves a phase constant, so you often see plus phi inside the parentheses. However, it turns out the phase constant is inconsequential when it comes to discussions of power. So when we're discussing the energy or power of sound waves, the phase constant makes no difference, so we often drop it from the discussion, but if you want, you could include a plus phi here. So this function is basically describing the displacement of individual air molecules, for example, as an audio speaker generates sound. Here I'm imagining an audio speaker as the source of the sound waves, but this could also be a person speaking, in which case your larynx or voice box would be the source, or this could be you simply clapping your hands. In any case, a source is generating sound waves by displacing the molecules from their equilibrium position, and as you can see, these molecules, through collisions with one another, transmit energy, and so ultimately energy, or a certain amount of power, propagates outwards in every direction from the source. The average power that is delivered to a particular area A is given by this formula. So we have the average power on the left, and on the right hand side we have 1/2 times rho, which is the volume mass density, times v, which is the wave speed, times omega squared, which is the angular frequency, times S max squared, which is the amplitude, and then A in this particular formula stands for area. So we're reserving the letter A for area, and we're using S max for amplitude. You might think it strange that area shows up in the formula for power, but you have to remember that sound waves are three-dimensional waves. So the energy of the audio speaker at the center of the sphere propagates outwards in all three dimensions and gradually spreads out over the surface area of the sphere. The cutaway of the sphere shows the peaks and the valleys. So the dark and bright bands that you see in this animation here represent the peaks and the valleys of the sound waves as they spread outwards. So the area over which that energy is being spread is important. If you want to know the average power delivered over the entire surface of this sphere, then for area you would use 4 pi r squared, which is the surface area of a sphere. On the other hand, you might be interested in the power that is delivered to one wall of this cubic box, for example, in which case you would have to know the area of that wall, and that's the area that would go into this formula. Now, we're not going to derive this formula for this course. I just want you to know how to use this formula. However, note that this formula is quite similar to another formula which we did derive. The power delivered by a rope wave was given by this formula. We derived this formula very carefully in a previous lecture, and note the similarity. Both formulas have 1/2 in them. For sound waves, we have the volume mass density because we're talking about a three-dimensional phenomenon. But for rope waves, we have the length mass density mu. For both waves, we have the wave speed. Now remember that the wave speed for sound waves is given by a different formula. For sound waves, v is equal to B, bulk modulus divided by rho. But for rope waves, we had a slightly different formula. It was tension divided by mu. So different formulas for the wave speed, but the wave speed does play a role in determining the average power. Both formulas have angular frequency in them. Both formulas have amplitude in them. Just when we were talking about rope waves, we used the letter A for amplitude. Now we're using S max. What's new for sound waves is that the area is important. With rope waves, the energy really had nowhere else to go. The energy would be generated at one end of the rope, and the only place it could go was the other end of the rope. With sound waves, the energy has three different directions that it could go, so the area over which it is spread is going to be important for us, so the area shows up in the formula for average power. In the previous lecture, we mentioned that the amplitude of sound waves is related to the loudness of those sound waves as perceived by the human ear. Here, we want to make that relationship much more precise. The perceived loudness of sound waves depends primarily on a quantity called the intensity of the sound waves. So intensity, denoted by the letter I, is defined as the power of the sound waves divided by the area over which those sound waves are spread. If you take the expression for power from the previous slide and plug it in here, you find that the intensity or the loudness of the sound waves is 1/2 rho v omega squared times the amplitude squared. So what we perceive as loudness actually depends on many different parameters. Certainly the amplitude is important, but the loudness of sound, as heard by human beings, can also depend on the angular frequency of those sounds. It can also depend on the density of the medium through which those sound waves are traveling. Note, however, that amplitude plays an important role. If you double the amplitude of a sound wave, then you are quadrupling the loudness or the intensity of those sound waves. A context in which the area is important is in human hearing. Humans hear things through their eardrums. So sound waves arrive at your ear, they impact the eardrum. You can think of the eardrum basically as just a thin membrane. It's roughly circular in shape, as shown here, and approximately 8 millimeters in diameter. So it's a very small membrane, but as sound waves arrive at the eardrum, they cause vibrations in the eardrum, oscillations, and those vibrations are then transmitted through the bones of the middle ear to the cochlea. The cochlea can then convert those vibrations or oscillations into nerve signals that are ultimately sent to the brain and finally interpreted as sound. But in this context, the area of the human eardrum is going to be important. The larger this area is, the more sound power that you can collect. The limits of human hearing are also important in this context. Human hearing has frequency limits, but it also has intensity limits. So here we're talking about the minimum and the maximum intensities that humans can hear. If sound has an intensity below approximately 10 to the minus 12 watts per square meter, then we usually cannot hear that sound. And if the sound has an intensity of above approximately 1 watt per square meter, then that's an extremely loud sound. For most people, that's considered a painful experience, and it could even cause damage to the structure of your ear. So this number here is often referred to as the threshold of pain. You don't need to memorize any of these numbers. However, if you plan to work with sound waves, designing hearing aids or audio speakers or headphones, for example, then these numbers are important numbers that you must be familiar with. So as I explained on the previous slide, what we perceive as the loudness of sound is related to the intensity of sound. And of course, intensity is in turn related to power and area. Unfortunately, sound intensity values can be awkward. If you remember, the minimum intensity, the lower threshold of hearing for humans, was something like 10 to the minus 12 watts per square meter. A lot of people don't like using scientific notation, sound engineers or audio technicians or otolaryngologists, those are ear doctors, prefer not to use sound intensity. Instead, they use something called sound level to describe the loudness of sound. Sound level is a more convenient measure of loudness, and it is defined by this equation here. So sound level is denoted by the Greek letter beta, and it is defined as 10 times the log of the intensity of the sound that you're speaking about divided by the minimum intensity that can be heard by human ears, which is 10 to the minus 12 watts per square meter. This logarithm is not base e, so it's not a natural log, it's log base 10. Now, in the previous slide, I mentioned to you that the minimum intensity that humans can hear is 10 to the minus 12. If you plug that number into this formula, you'll get 10 to the minus 12 divided by 10 to the minus 12, which is just 1. Log base 10 of 1 is simply 0, so the minimum sound level that humans can hear is simply 0. I also told you that the maximum sound intensity, the threshold of pain, was approximately 1 watt per square meter. If you plug that number into this formula, what you get is 120 for the sound level. So this is considered the maximum sound level that humans can hear. The unit that is assigned to sound level is known as the decibel, and it's denoted by lowercase d, uppercase b. The decibel is 1/10 of a bell, and the bell is named in honor of Alexander Graham Bell, who invented the telephone. Although that history is not so important to us, just know that the unit for sound level is the decibel. You don't have to memorize any of these numbers, but it's good to know that a typical conversation between two people standing approximately a meter apart is going to be around 60 decibels. A loud police siren or a jet engine flying by might have a sound level of approximately 120 or 130 decibels. The beating of your heart or the breathing of a very quiet person is going to be something very low, like 10 decibels, barely audible. And of course, 0 is the absolute minimum threshold of hearing when measured in terms of sound level. So as we've discussed, what humans perceive as loudness depends on many different parameters. Sometimes that loudness is measured in terms of sound intensity, and sometimes it's measured in terms of sound level. Those two concepts, of course, are interrelated. What makes the discussion of loudness a little more complicated than expected is the fact that human hearing has a non-linear response to sound. In fact, this is true of most human senses. Your sense of vision and your sense of taste, even your sense of touch, tend to respond in a very non-linear way to external stimuli. And this is primarily because the human brain tends to become desensitized to stimuli. You may have noticed that when you first arrive at a concert and stand next to some loud audio speakers, the sound might be uncomfortably loud, but 15 minutes into the concert, you've acclimated and now the sound no longer seems too loud. We describe this phenomena by saying that human hearing is non-linear, meaning that doubling the power or the intensity does not necessarily double the perceived loudness. Roughly speaking, humans perceive a sound as becoming twice as loud when the intensity is multiplied by 10 or when the sound level is increased by decibels. So some people tend to prefer talking about intensity. Others, especially, for example, ear doctors, prefer talking about sound level in terms of decibels. So you should know that when you add 10 decibels to the sound level, you're basically making the perceived loudness twice as great. Or if you multiply the intensity by 10, you're achieving the same effect. You're making the loudness twice as great. So let's end this lecture with a practice problem. A concert loudspeaker generates 100 watts of acoustic power. Assume sound waves propagate in every direction in 3 dimensions. What is the sound level at a distance of 10 meters? So imagine you're at a concert and you're standing approximately 10 meters away from a relatively powerful concert speaker. This audio speaker generates 100 joules of energy every second. Remember, a watt is a joule per second. We're going to assume that this energy spreads out in every direction like a spherical wave. Technically, that's not true. Most audio speakers are designed so that they broadcast most of the energy in the forward direction and less energy propagates backwards or to the sides. The box of the speaker or the casing of the speaker basically prevents some of the sound from propagating backwards or to the sides. However, for this problem, we're going to ignore that effect. We're going to assume that the 100 joules of energy that is generated per second is going to spread out over the surface of a sphere. So these sound waves are going to be spherical waves that are going to propagate outwards with the center located at the location of the audio speaker. So we're interested in the sound level 10 meters away. To calculate the sound level, we need to calculate the intensity. Intensity is power divided by area. And the area is going to be the area of a sphere, which is 4 pi r squared. The radius of that sphere is going to be 10 meters. We're assuming that the source is at the center of the sphere, and we're interested in the sound level 10 meters away. So we're imagining that the area is the area of a sphere whose radius is 10 meters. In other words, this energy has now spread out over a large sphere whose radius is 10 meters. When we plug those numbers into our calculator, we find that the intensity is 7.958 times 10 to the minus 2 watts per square meter. So power per unit of area. To calculate beta, which is the sound level, we need to use this formula here. I is the intensity that we just calculated, and I min is the minimum intensity that the human ear can hear, which is 10 to the minus 12. We plug those numbers in and we find that at a distance of 10 meters, the sound level is approximately 109 decibels. So this is not entirely quiet, but it's not really loud either. Remember that the threshold of hearing has an upper limit of about 120 decibels. So this is not painfully loud, but it's a relatively loud concert. Now, suppose you're interested in knowing whether the sound is going to damage your hearing. Now, damage to hearing is a complicated question which involves a lot of biological factors, but your starting point would be to calculate the power delivered to the human ear. More specifically, let's calculate the power that is delivered to one human eardrum at a distance of 10 meters. So what is power? Well, remember that intensity is power divided by area. Rearranging that equation, we find that power is intensity times area. We've already calculated the intensity at a distance of 10 meters. The intensity was given by this number here. But now we're interested in not the total power that is spread out over that 10-meter sphere. We're only interested in the power that impacts the eardrum. The human eardrum, at least one of them, has an area of 5 times 10 to the minus 5th. So when we multiply those together, we find that one eardrum receives 3.979 times 10 to the minus 6 watts of power. This is typically not enough to damage your hearing, but if you are interested in knowing whether sound is doing damage, you would start with this number. You would calculate the energy or the power that each eardrum is receiving, and then that would tell you whether the eardrum or the bones that are connected to it are going to be damaged or not. And that is the end of this lecture. Thank you for your attention.